Let's look at LRC circuits and how they behave at high frequency and low frequency limits. So here we have just a random LRC circuit. It is no longer in series, as you can see. This circuit is powered by a generator whose voltage and current alternate with a frequency F. Now, remember that the inductor has a reactance that is directly proportional to the frequency of the current in the circuit, and the capacitor has a reactance that is inversely proportional to the frequency of the current in the circuit. So if we looked at high frequency limits, then when frequency is very high, then the inductor is going to have a very high reactance, and it will behave like a broken wire, like a broken circuit. When the frequency is high here, then the capacitor will have a very low reactance, so it's not going to impede the current flow. That's why we'll say that when the frequency is high, the inductor breaks the circuit. It doesn't let current flow through it. But when the frequency is high, the capacitor acts as a wire. It does not impede the current flow. The opposite is true at low frequencies. So when frequency is low, the reactance of the inductor is going to be low as well, whereas when the frequency is low, the capacitor is going to have a very high reactance. So then we'll say that the inductor acts as a wire at low frequencies, and the capacitor breaks the circuit at low frequencies. Let's see how exactly we apply this. Let's look at high frequency first. So at high frequency, the inductor breaks the circuit. So instead of an inductor, we're going to have a gap here. There won't be any current flow through the inductor at high frequencies. But at high frequencies, the capacitor acts as a wire. So instead of having a capacitor here and there, we're going to replace them by plain wires. So here we have the wires that let current through unimpeded. What that means is that when the generator provides current, the current will flow here, it will split up into these two branches, it will recombine and return to the generator, so then that current can flow through the circuit for an extended period of time. Then when we apply Ohm's law, the VRMS really is equal to the RMS current through the circuit times the equivalent resistance of the circuit. Now in this example, the equivalent resistance is actually the resistance of two resistors in parallel, and that would be 1 over R plus 1 over R, so that when we do the math, we end up with the voltage being current times resistance divided by 2. But it's not really the voltage that we're interested in, because the voltage is set based on the frequency. What is changing is how these components behave in the circuit and how they affect the current. So then when we're looking at the current through the circuit, what we're left with here is twice the voltage divided by the resistance at high frequencies. And that's because the capacitors behaved as wires and the inductor behaved as a broken wire. Now let's look at the same thing at low frequencies. So here we have the new circuit, because at a low frequency, the inductor acts as a wire. It doesn't impede the current flow. So here we have the wire where we used to have an inductor. But then the capacitor breaks the circuit, so there is no current flowing through the capacitors here anymore, and this is the circuit we're ending up with. That means that when current is being pushed by the generator, it'll go through here. It can't go through the capacitor because there's nothing there. It doesn't complete a circuit, but the current will go through here, through this resistor. It can't go through there because, again, it's a broken circuit. It will turn and go through the resistor, through the inductor, and it will complete the circuit. Then, by Ohm's law, the RMS voltage in the circuit is equal to the current through the circuit times the equivalent resistance. This time the resistors are in series, so we have voltage is current times the sum of the resistors. And that means that the voltage is 2I times R. But again, what we're interested in is the current more than the voltage, because the voltage was set And now with a different set of components here, the current will change. So for low frequency, the current will be voltage divided by 2R. So you see how at high frequency and at low frequency, the currents behaved differently because of the way that capacitors and inductors acted as a function of the frequency. Now, this is just one example. There could be various different kinds of combinations of resistors, capacitors, and inductors in a circuit. This is just one particular example to explain the theory.